Hi, I'm honored to receive the Research Excellence Award from the ACP, and I'd also like to thank the constraint programming community for inventing such a fascinating field that's been so much fun to work in over the years. I got involved in CP in the early days of the field. I was part of the operations research world at the time, but I found the ideas of CP very interesting, particularly because they used logic as a tool for problem solving, which I always thought should be an option. I think that logic and optimization have always been closely related, and I think that constraint programming not only reveals some of those connections, but takes advantage of them. So I thought it might be fun to have a look at some of the relationships among these three fields. The deep connections between logic, optimization, and CP go back at least to George Boole, so I'd like to attempt a brief retrospective of this history. Now, there are many people who have made major contributions to these three areas, and obviously I don't have time to mention everyone, unless I talk for hours, and I don't think we want that. So I've adopted the rule of only mentioning by name those who are no longer living. So if I don't mention you by name, this is a very good sign that you're not dead. So this is the spaghetti chart I'd like to use. I know it can give you eye strain, but don't worry, I'm going to take you through this piece by piece and try to make sense of it. So as you see on the left, we have primarily ideas in logic, and on the right, ideas in optimization. And in red, we have ideas from constraint programming, and the green lines show some of the connections among them. So I'm going to start with the stream of research that's probably most familiar to this audience, and that is the one that takes us through logic programming. This is shown by the heavy lines on the left, and also one connection with integer programming. Boole actually advanced a project that was begun by Gottfried von Leibniz, a very famous philosopher, although Boole apparently wasn't aware of this until late in life. Leibniz believed that all of science can be formulated in a single logical language, in which implications of science can be obtained by calculation. And his invention of the calculus, along with Newton, the calculus of infinitesimals, is an example of that. Boole did the same thing, only he implemented Leibniz's project up to a point. He devised a language in which you can't actually calculate logical inferences. Now, curiously, Boole's work was largely forgotten for a century, with at least one exception, and that was the philosopher Charles Sanders Peirce, who read Boole's work and extended it. Peirce made several innovations. We're going to talk about a couple more later, but one thing he did was to help advance logic toward a system of quantified logic, or first-order logic. Boole started the project by introducing multiplace predicates. Peirce added logical quantifiers like for all or for some, and the first fully formed first-order logic was developed by Gottlob Frege in the late 19th century. In the early 20th century, there were a number of important developments by people like Leeuwenheim, Skolem, and Herbron, particularly the famous Herbron's theorem, which students always learn in Logic 101, a compactness theorem. And interestingly, there is an almost identical theorem in integer programming. The theorem states that if we have an infinite constraint set that's infeasible, then some finite subset of that constraint set is infeasible. Now, as you know, logic programming was an attempt to combine declarative and procedural modeling in the framework of quantified logic. So in a logic program, such as Prolog, you can read the statements as declarative statements that describe the problem, or as stating a procedure for solving the problem. This later, of course, became a fundamental idea in constraint programming. A key step in first-order logic is unification, which is basically a constraint-solving exercise. It tries to equate two instantiations of a formula by appropriate substitution of constants. Well, it's not a big step to extend this to other types of constraints. And in Prolog 2, we see disequations as well as equations in unification. And later work added a number of other constraint sets, such as arithmetic constraints and so forth, and this eventually gave rise to the global constraints of constraint programming. Constraint propagation developed because it's important to draw the implications of a set of constraints rather than just single constraints. Implication of single constraints, of course, gives rise to filtering methods. At the same time, in the constraint satisfaction literature, we saw the development of consistency concepts and how they connect with backtracking. Now, how does the SAT community fit into this, the satisfiability problem? Well, you see the chain here, starting with Boole again. We go down through SAT, and there's a connection with Binder's decomposition. Although I've been talking about first-order logic, much of Boole's and Peirce's work deals with so-called ground-level propositions in first-order logic, or in other words, propositional logic. In the 1950s, a philosopher named Willard Van Orman Quine proposed a method for simplifying propositional formulas. And it's in fact a complete inference method for propositional logic. When you apply this to conjunctive normal form rather than disjunctive normal form, the method becomes resolution. And resolution became a core element of the famous Davis-Putnam algorithm, which was used to check validity in first-order logic. Now, resolution was later replaced by more efficient methods, but it has important theoretical connections with other ideas, which we'll discuss shortly. In any case, the outcome of this research was today's powerful methods in the SAT community, which we're going to see again is related to Binder's decomposition. Decision diagrams also came from Boole through the path you see here. It's not well known that Peirce applied Boole's methods to switching circuits. This was in the 1860s. Again, this work was forgotten for decades, but a young undergraduate student named Claude Shannon at the University of Michigan was required to take a philosophy course. I'm not sure he wanted to take the course, but it exposed him to Peirce's work. And he got the idea for applying Boolean logic to electronic switching. And of course, this was the basis for his famous master's thesis out of MIT. Probably the most famous master's thesis ever written by far, and the foundation for our world today, the computer age. Well, in the meantime, this work with switching circuits gave rise to binary decision programs that were designed to calculate the output of switching circuits. And these programs were later represented with diagrams, binary decision diagrams, which we now know provide a unique representation of a Boolean function if the ordering of the variables is fixed. Today, decision diagrams are being used both for filtering and constraint propagation in CP. They also provide a comprehensive framework for optimization. So if you look at the 6 elements of optimization shown in this diagram, each one of them can be carried out by decision diagrams. From modeling, where decision diagrams use recursive formulations, search, primal heuristics, constraint propagation, relaxation, and post-optimality. Now, another little known aspect of Boole's work is probability logic, so I'd like to say a word about that. He actually considered probability logic to be his most important contribution, and if you look at the title of his major work, The Laws of Thought, you should read the rest of the title, on which are founded the mathematical theories of logic and probabilities. Now, what's the connection with optimization? It was shown by Halperin in the 1970s that Boole's probability logic actually has a linear programming model. It was perhaps the first application of linear programming, although linear programming wasn't explicitly applied. Nielsen proposed almost the same model in the 1980s in the AI context. And another interesting fact is that this LP model can be solved by column generation, which is based on Danzig-Wolf decomposition, which in turn is based on duality, a concept we'll mention later. Filtering, let's have a look at that. So here, filtering actually can be seen as coming through the optimization world in the following way. So Joseph Fourier developed a theory of linear inequalities and a method for solving them that provides the foundation for linear programming. The solution method was independently rediscovered by Motzkin and is now called Fourier-Motzkin elimination. Kantorovich in the late 30s developed a linear programming optimization problem. Actually, the term linear programming was introduced by George Dantzig, who independently developed linear models during the 1940s. Of course, Dantzig devised the famous simplex method for linear programming, which is a major improvement over Fourier-Motzkin elimination and remains the method of choice today for most applications. Restricting some of the variables to be integer is a natural development, and that gave rise to integer programming. Another outgrowth of linear programming is a special case, and that's network flow theory, which also developed in the electrical engineering community. And as I'm sure you know, network flow theory has been widely applied to filtering methods in CP, beginning with the all-different constraint. And duality is an important part of that application. Also, integer programming and optimization led to the study of combinatorial optimization problems, beginning with the traveling salesman problem. And one outgrowth of that work was an edge-finding algorithm for single machine scheduling, which was published in an OR journal, Management Science. And that was the springboard for the powerful domain reductions we now see for cumulative scheduling and other constraints in the CP world. Now let's have a look at duality, which I've mentioned several times so far. Duality again arose from linear programming and follows this path and has connections with CP. The story is quite interesting. I heard the story from George Dantzig himself, so I assume it's true. By chance, he met John von Neumann, famous mathematician, on a rail platform in Princeton Junction, New Jersey. And they got to talking and discovered they both were working on what we now call linear programming. Von Neumann was a pioneer in game theory, and he was working on a two-person non-cooperative zero-sum game. And after talking with Dantzig, they both realized that this game theoretic problem was a linear programming problem, in which one player solves the so-called primal, the original problem, and the other player solves the dual of the linear programming problem. Duality has become a very powerful idea in optimization, and a beautiful one as well. You see it in applications of Lagrangian methods introduced many years ago by Joseph-Louis Lagrange, as well as in Dantzig-Wolf decomposition, which gave rise to column generation, widely used today, and Bender's decomposition. There are many forms of duality and optimization, but they are all special cases of a single concept, which we can call inference duality. Basically, the original problem can be seen as a search problem that finds the best feasible solution. The dual problem can be seen as an inference problem that infers the tightest possible bound on the objective function from the constraint set. And the solution of the dual problem is a proof. The type of dual you get depends on the type of inference method you used to derive bounds on the objective function. If that inference method is non-negative linear combinations, then you get the classical LP duality. If the inference method is complete, then you get a so-called strong dual for which the optimal value is the same as the optimal value of the primal problem. Now here are the best known duals in optimization, the linear programming dual I mentioned. The Lagrangian dual uses the very same inference method of LP, but applied to nonlinear problems. A slight change in that inference method gives rise to surrogate duality, which is actually stronger than Lagrangian. And if you use a cutting plane method, namely Schwarzschild-Gomery cuts, you obtain the subadditive dual, which is a strong dual. These two strong duals are based on the two fundamental theorems of their respective fields. The linear programming dual is based on the Farkas lemma, and the subadditive dual is based on Schwarzschild's theorem, which is the fundamental theorem of cutting plane theory. Now, as I mentioned, Bender's decomposition is one application of duality. It was originally designed for mixed integer programming problems that become linear after some of the variables are fixed. The dual of the subproblem provides the Bender's cut That is a constraint that excludes undesirable solutions. Now, if you generalize that dual to the inference dual, then in principle you can apply benders to any kind of problem because the subproblem need not be a linear programming problem. And you obtain the bender's cuts by analyzing the proof of optimality for the subproblem. The result of this is logic-based bender's decomposition, so-called because it relies on logical inference in the dual. It's been applied to a number of problems, but more relevant to our purpose is that it has become a vehicle for combining optimization with constraint programming. So typically, the master problem in benders is solved by an optimization method like mixed integer programming, and the subproblem solved by CP, particularly if it's a scheduling problem, since CP offers the state-of-the-art for many scheduling problems. There's also a very nice connection with satisfiability, as I mentioned earlier. The conflict clauses that form the heart of the SAT algorithms are actually logic-based bender's cuts, none other than bender's cuts. And the inference method that gives rise to these bender's cuts is unit resolution, a restriction of the resolution method. The bender's cuts are obtained from a proof of infeasibility by analyzing a conflict graph. So here we have another remarkable set of connections between logic and optimization. Now I'd like to wrap up by recounting some of the connections between cutting planes and concepts in CP. It again began with Fourier-Motzkin and followed the path you see here. So Fourier-Motzkin elimination is actually very similar to the resolution method I mentioned. So here's resolution of two logical clauses giving rise to a resolvent. Okay? In effect, this is a projection method that projects out the variable x4. Now, if you write these clauses as inequalities and take a linear combination, then you find that resolution is just Fourier-Motzkin elimination, except that you round up the right-hand side of the result. We not only have that connection, but resolution lies at the very heart of integer programming. And that's because a resolvent is a rank-Wunsch-Fatal-Gomri cut. And the fundamental theorem of IP, which I mentioned earlier, states that any valid cutting plane can be obtained by generating rank-Wunsch-Fatal-Gomri cuts. If you look at the proof of this fundamental theorem, you find that the resolution algorithm is the key to the proof. So a basic element of logic, namely resolution, turns out to lie at the very heart of integer programming. Of course, cutting planes play a major role in the solution of IP and other problems, but there's something else. They also achieve consistency. How? Well, we can view a consistent constraint set as one in which any infeasible partial assignment violates a constraint. And of course, you can avoid backtracking that way. So here's an example, a little 0-1 constraint set. It's not consistent because setting x1 equals to 1 violates no constraint, but it cannot be extended to a feasible solution. And as a result, you get backtracking. If you add a cutting plane, here's a cutting plane, then now it's consistent because fixing x1 equals 1 violates one of the constraints. A concept of consistency more useful in integer programming is something we might call LP consistency. A constraint set is LP consistent if any infeasible partial assignment is infeasible in the LP relaxation of the problem. So for example, here we have the same problem. It's not LP consistent because setting x1 equals to 1 is feasible in the LP relaxation. That is, it's feasible in the polyhedron defined by the red lines. But if you add a cutting plane, then we have LP consistency because setting x1 equals to 1 is no longer feasible in the LP relaxation. Incidentally, this cutting plane is not just any cutting plane. It's a rank-Wunsch-Fatal-Gomri cut. And in fact, there's a theorem that an IP constraint set is LP consistent if and only if all implied clausal inequalities, that is, all inequalities that represent clauses, logical clauses, are rank-Wunsch-Fatal-Gomri cuts. So this provides a new perspective on cutting planes. As far as I know, in the last 50, 60 years of research on cutting planes, this idea has never emerged. Traditionally, cutting planes are used as separating cuts, that is, they cut off fractional solutions, but they can also be used to cut off infeasible partial assignments, and we might call those consistency cuts. So I hope you found this interesting and fun, and I thank you for your attention.